So out of 90 points, the mean was 65, and the median was 67. Max was 90. Standard deviation 12. So average was 65. We've got this is the histogram by letter grade. So this is 90. Charles, A is 90. 90. Okay. 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 So let's. I wanted to go over this. I posted. By the way, I posted all the answers online right there. I think I posted a link in the forums too. I want to bring up the exam without the answers. Okay. So 2's complement. So for the first question, convert the following 2's complement number to decimal. The first thing you want to notice here is it's 2's complement and the most significant bit is 1. That tells you right there that this should be a negative number. And if you remember from the slides, there's a couple ways to do this, but the easiest I think is to observe that this is a 6-bit number, right? 1, 2, 3, 4, 5, 6. And in a 6-bit 2's complement number, the most significant bit represents negative 2 to the power of n minus 1, right? So in this case, n is 6, n minus 1 is 5, 2 to the 5th is 32. So that first, don't show that again. Yeah. That first bit being 1 means negative 32. And then the other bits just have their normal meaning. So this is negative 32 plus 1. So this should be negative 31 is the value. Some of you guys converted it, did a 2's complement conversion to make it positive, in which you would invert all the bits and add 1, and that would work too. But I think the easiest way is to just assume that first bit is negative 32, and then you would just add 1. Okay, any questions?
So the answer was 32 or 33?
It was negative 31. It's this first bit is gives a value of negative 32, and that last bit gives a value of 1. So you would add the 2. So negative 32 plus 1, negative 31. Okay, so the next one, this one's a little bit tougher. 2's complement is 71. You can just take 71 and do a little conversion. So 71 divided by 2 is 35 with a remainder of 1. Right? 35 divided by 2 is 17 with a remainder of 1. Right? 17 divided by 2 is 8 with a remainder of 1. 8 divided by 2 is 4 with a remainder 0. 8 divided by 2 is 4 with a remainder 0. 4 divided by 2 is 2 with a remainder 0. And then 2 divided by 1 is 1 with a remainder of 0. Right? So then you read from the bottom to the top. It's 1, 0, 0, 0, 1, 1, 1. Right? Now we can double check that. This is bit 0, 1, 2, 3, 4, 5, 6. So this is 2 to the 6 plus 2 to the 2nd plus 2 to the 1st plus 2 to the 0th, which is 64 plus 111 is 7. So that should give us 71. So that allows us to double check it. Now to convert this to 2's complement, we have to invert all the bits. So this becomes erase this stuff here. So this becomes 0, 1, 1, 1, 0, 0, 0, and then add 1, 0, 1, 1, 1, 0, 0, 1, right? But the thing is that the sign bit here would would be 0, right? And we know that this is supposed to be negative, so you have to add that sign bit there, right? Does that make sense? Now you might say, why do you have to add a bit? Well, it's because when we converted 71 from decimal to binary, we got 1, 2, 3, 4, 5, 6, 7 bits. That was the minimum number of bits to represent 71 as an unsigned number. But to make it 2's complement, we had to add that extra bit because whenever the 2's complement requires the sign bit, right? So this number 71 is a 1, 2, 3, 4, 5, 6, 7-bit number if it's unsigned, but as a 2's complement, it has to be an 8-bit number, right? Because the 8 bits gets us from negative 128 to positive 127, right? OK, any questions? All right, next question. How many 6-bit 2's complement numbers are less than 0? This one is if you have a 6-bit number and 1, 2, 3, 4, 5, 6. If the first bit is 1, it means it's negative. So basically what you're left with is 5 bits, right? And 2 to the 5th power is 32. There's 32 negative values. So that a 6-bit 2's complement would give you a range of negative 32 to positive 31. So there'd be 32 negative values. So how many truth tables exist for a Boolean function having n 1-bit inputs and a single 1-bit output? So for this, a truth table, if you have n inputs into a truth table, there are 2 to the n, was it capital N? Yeah, 2 to the n rows in the truth table, right? Each one of those rows has an output bit. So if we want to look at all possible output bits, you're basically just looking for a 2 to the nth power number, of which there are 2 raised to that power, right? In other words, to visualize this a little bit, let's assume that we have a 2-bit truth table. A 2-bit truth table has 4 rows, right? So because there's 4 different input possibilities. So then the output kind of looks just like a 4-bit number, right? So if we want to look at every possible truth table, we could have all zeros, or we can have 0001 or a 0010 or a 0011 or 0100 all the way up to 1111. And so there are 16 of these, right? So the number of possible truth tables for n inputs is 2 to the n to get the number of rows, the number of output bits. And then you have to say 2 to the 2 to the n to get all the possible output bit values, right? So this question was essentially just asking you how many values you could store in a number that has 2 to the n bits is really what it was asking you, right? So it's 2 raised to the 2 raised to the n. And so if n is 2, then that's 2 raised to the 2 raised to the 2, or 2 raised to the 4, or 16. So there's 16 truth tables for a 2-bit function. Any questions about that? OK, now the next one is, I made it a bonus because the question was, how many Boolean functions of 2 variables can be built as a single Cmos logic gate? So the rules with Cmos is that, remember that a Cmos gate has it consists of, has an input, has inputs, right? And then those split off and they go to a pull-up network and a pull-down network. Okay, and then these guys give you the output. And the pull-up network is responsible for setting the gate's output to 1, pulls up the VDD. And the pull-down network is responsible for setting the gate's output to 0, right? But the trick is that the pull-up network has to be made with PMOS transistors which only turn on with a 0. So what that means is that any case where the gate has to put an output of 1 means that you have to have at least one input that's a 0, right? So if you have what that means, and likewise, anytime the gate puts out a 0, anytime you have to pull down to ground, you have to have at least one 1-bit input. Otherwise, you can't activate the pull-down network unless you give it at least one input that's a 1 that will turn on an NMOS transistor, right? So PMOS transistors turn on with a 0, and an NMOS turns on with a 1, right? And PMOS is the pull up and NMOS is the pull down. So what that means is if you look at the truth table here, 0, 0, 0, 1, 1, 0, 1, 1 for your inputs. If I'm putting a 0, 0 into this gate, that means that there's no possible way that I could pull up the output of this gate to 1. Impossible. Sorry, I screwed that up. There's no way I can pull it down to 0, right? Because this would mean that all NMOS are off, right? Because remember, NMOS turns on with a 1. There's no way to turn on an NMOS transistor and no way to activate the pull-down network if I'm putting all zeros in, right? Meaning that this has to be a 1. I have to put a 1 out. Likewise, if the inputs are 1, 1, I don't have any zeros, there's no way to activate the pull-up network. There's no way to get a PMOS to turn on. So this guarantees that all PMOS are off this row, right? Meaning that this has to be a 0, leaving only 2 empty slots that I could set however I want. So because this essentially is a 2-bit number now I can set, so this is 2 to this 2 equals 4. So there's 4 different gates I can build with CMOS gates. Does that make sense? Right? Now I made this a bonus question because I didn't really focus very much on this, but this was something that was in chapter 1. Okay, this one is a 2-dimensional transfer function, and the first question is, what Boolean function does it perform? This one was a little tough. But basically, if you look at A and B, if A is 3, like if A is high, and say B is low, you're in let's see, A is high, right, and B is low, which means you're in this quadrant.
So that's what that is.
Right? So obviously the output is, if you have A is 1 and B is low, you're in this quadrant, meaning that the output is high, right? So let's figure this out. A, B, out, what is it, Y? Y. Okay, so A is 3, B is 0, you're in this quadrant, that looks like a 0, right? So A is 1, B is 0, I got a 1. Everyone see that? Likewise, if A and B are both 0, so A is 0, B is 0, I'm in this quadrant, that's a 0. Okay, and then if B is high, B is 3, and A, so B is up here, A is down here, that looks like a 1, right? That's this quadrant, that's a 1. Now the problem is if they're both high, if A is 3 and B is 3, they're both high. Well, it's kind of hard to tell, but the output clearly isn't 1, right? Because if it was 1, I would have a surface up here, right? That would be equal to these guys. So it must be 0, right? So that is that's an Xor gate. Everyone see that? Right? It really has to do with looking at the 4 quadrants of the xy plane and matching up the corresponding y value. Make sense? Sorry? An XOR gate is a modulo 2 operation. If you give it an odd number of 1 bits, it'll give you a 1 output. XOR gates are a little strange because the problem is, again, you can't make one in a CMOS, right? Because if A and B are both 0, there's no way I can pull the output down to 0 because all my NMOSs would be off, effectively disconnecting the output from ground. So you can't make an XOR gate as a CMOS gate. You can only do it as, with multiple gates. What about an XNOR? An XNOR would be the opposite of that. And yeah, likewise, you can't do an XNOR because a 1-1 could never pull up to, would turn off all the PMOSs, so I would never be able to get a 1 output. So you can't build an XOR or XNOR with the CMOS. But anyway, that's beside the point. Yeah, so this is an XOR. If you answered OR, you still got full credit. So in XOR or an OR, fine. Okay. Now, what are the approximate values of VIL, VOL, and ML? Well, in terms of the output low, that's clearly 0, right? Right, because of this. Because of this, you can see, because this line on the y-axis here, well, this y-axis, the output axis, it goes all the way down to 0, right? So that means that VOL is 0. Now, what about the input? Well, for the input, I can look at A or B. I think now it's a little hard to read. So if you got anywhere near the answer here, we gave you full credit. But if you look at this really closely, it looks like these are, and it's hard to tell on the projector, it looks like it looks like this B, for instance, is 1.25. It looks like when B becomes 1.25, and of course A is low, right there. So right at this point where this starts to go up is when A is 0 and B is 0, but B is starting to transition over from 0 to 1, and thus Y is transitioning to 1. That happens at about 1.25 volts, right? So anything over 1.25 volts on B is registering as a 1 because that's causing Y to go high. Likewise on A, I think it's 1.5 on A. And you might say, why are A and B different? I don't know. You can tell they're different, though, because the surface area here is different from the area here. So I said in the question, if A and B thresholds are different, use the lower one. So I think V input low is 1.25. Right? That's our threshold. That's when things change. And so the noise margin is just the difference, so it's 1.25 volts. 1.25 volts is the noise margin. Basically, the difference between the low for the output versus the low for the input. That represents how much noise we can add to a wire and still have it work correctly. OK, circuit below. This one, there's a few different ways you could have done this one. The way I did it was I said, well, if A and B are 0, 0, then C and D don't care. Now, by the way, this concept is going to become a lot more important going forward because this is really using muxes this way are the way that you build up a CPU design. So, and this comes up a lot in CPU design where C and D are inputs, but if A and B are both 0, then the output of this mux is a don't care. It's going to get blocked. You see what I mean? Because if A and B are both 0, I'm going to select this top input. I'm going to ignore the 2 inputs that are being fed by this mux. You guys with me on this? So what that means is Y has an implicate that is just not A and not B. Because if A and B are both 0, then automatically Y is 1. I don't care about anything else, right? Or if A and B are 0, 1, meaning not A, B, if that's the case, and if that's the case, what's happening is that if A is 0 and B is 1, then I am going to take whatever comes out of this mux, in which case C and D now become relevant. But the only time that it could be a 1 is if C and D are both 0, which means I bring in this hard-coded 1. So not C, not D. So not A and B selects this input. And then if C and D are both 0, not C and not D, then I'll be taking this VDD, routing it through this mux, and then through this input over to Y. Likewise, if A is 1 and B is 0, and C and D are both 0 again, that will also give me the same result. Because in that case, C and D being 0 brings in this VDD. A and B being 1, 0 routes it through this input and then over to Y. Right? So a mux is really a way to steer data, really. It's a way to route data. And this would be the Boolean logic for doing that, the equivalent Boolean logic. Yes?
Would that also be the minimize SOP form?
Could you minimize that anymore, right, is the question.
Be in the second implicate and the A and the third implicate were redundant, you can get rid of those. Because if you have A not, B not, then you already just go to the first implicate. I found the same thing.
Mm-hmm. Right.
The Carnot math works out that way.
Yeah, it's really just either if A is not and B is not, and then the opposite for the other.
So if A not B not is true, meaning they're both 0, then I select this implicate, right? Right? Are you saying factor out C and D from these two?
Get rid of the B in the second implicate and get rid of the A in the third implicate.
Oh, these guys.
Yeah.
Yeah, that could certainly. That's a good question. How would that work out? That could be the case. Yeah. One way to be sure is if you did a Carnot map.
Yeah, I did do that.
Did you do a Carnot map?
I also did the same.
Okay. Yeah, I mean, you could also do that through applying Boolean theorems. I'm not sure exactly. I can't think off the top of my head though how you'd do that. But yeah, that could easily that could be the case. If you had this though, you would get full credit. And if you had an equivalent minimized form, hopefully you also got full credit. If not, let me know. You didn't get full credit? Okay.
Wouldn't like the A and B in the second two parts, since they were both like opposites of each other, like just get rid of each other, you can just write the A not B not plus C not D not.
Well, let's find out. That's a good question. Let's see if I could fit this. 0, 0, 0, 1, 1, 1, 1, 0. This will be A, B, C, D. So if A and B are both 0, then those are all marked off, right? If you've got not A and B, which is this column, and C and D are both 0, that would be this guy, right? And so then if you've got A not B, which is this column, and also here. Yeah, so I think what James was saying was you can circle these two guys, in which case you don't care about B. Right, so you're right. Yeah, you can get rid of B there, right? And then these two guys, the outside, right, which allows you to get rid of A. Correct. That's right. Yep. Good.
So you could just write A not B not plus C not D not?
A not B plus
A
A not C not D not, or B not C not D not. That's right. Yep. That's right. Yeah, if you had this correct. That's right. Works too. Yeah, that's even better. That's better than my solution. Yes? Sorry? Sure. What's your name? Sorry? Oh, yep. There you go. Okay, great. Yeah, yeah. So either answer is good. All right. Next one is the next question asks you to synthesize this into gates. So, so I think I said assume that you have the negated form of the inputs. So not A, not B goes into an AND gate. And then we've got not A, not C, not D going into an AND gate.
Actually, in the rule it says a gate can have no more than 2 inputs.
Yeah, I was going to get to that. We're gonna transform it. So let's go not A, not C, not D. Yeah, so that's a good point. That would give us a 3 input, which we have to fix. And then we had what was it? B, not C, not D. Was that it? Not B. And then these guys go into an OR gate, right? So that's the circuit, but it violates at least one of the rules there. We don't want to have any 3-input gates. So there's a number of ways you can fix this. We can take out this not C, not D, right? We can make that its own little gate, right? And when we can use the the associative rule that says that we can just do that, right? You guys with me? Does it make sense? And then for this OR, it's the OR, we can just simply break that OR into a cascaded OR like that, where we have two input OR gates cascaded as opposed to the 3-input OR gate. So that's one way to do it. There's other ways as well. Yes?
Can you explain the second caveat?
Do not use more than one gate of the same. Right. So that would be if you had 2 of these guys, right? What I wanted you to do was take advantage of Boolean sub-expressions that have already been calculated by another gate, and then you can just fan them out. You can split them out and share. The purpose of this question was to get you thinking about how to build logic circuits that are not in the typical 2-level format. The product of sums of product, where you go through 2 levels of gates, even though those gates can grow huge. This is a trade-off between number of gate inputs and the latency, the critical path having to go through this, right? Because now we have to go through 1, 2, 3, 4 levels of gates, right? So, this is to get you thinking about that not all Boolean logic circuits are 2 levels. Okay, and also you can do the fan out and share inputs. Okay, so this question was pretty standard. This says write a Boolean. I think there was a very high success rate on this. I think most everyone was comfortable with this. Write a Boolean equation in sum of products canonical form to describe the function shown in the table. The first thing you want to notice here is that there are 1, 2, 3, 4, 5, 6 rows of this truth table that have a 1 output. That means you should have 6 minterms, right? And then you can just build out the minterms by just looking at those 6 rows and then building your minterms according to the values of A, B, C, and D. So this first one would be not A and B and not C and D, right? And then you go to the next one, do the same thing, and you add them all up. Okay, so you should have 6 minterms there. Yes?
So did you take off points if they just put B, D, instead of putting the not A and not C?
Yeah, we need the minterms, the canonical form. The fact that I said canonical form and using only minterms means that each one of your products has to contain all 4 variables, which seems kind of unnecessary if you can minimize it, but that's the canonical form.
Okay.
That's the point of the canonical form is that it follows that well-defined format. Now the product of sums, every time I see POS, I think of something else. Product of sums, canonical form, same idea, except now you just look at the rows with zeros. So there's 1, 2, 3, 4, 5, 6. Oh, look at that. There's also 6 zeros in there. And in that case, when you convert the input values to the max terms, you have to negate each individual value. Right? So in this case, the first one would be A is a 0, so it would be not negated. It would be A or not B. Or C or D. Right? And then you would AND that with the next one of the 6, which would be the next 0. So you got to skip down to this row. That would be A or not B or not C or not D, and so on. You do that for the other. So you'll have all 6. Okay? Bottom line is that you ignore the don't cares because this is the min terms and canonical form. The minimized SOP would allow you to incorporate the don't cares in there in order to, and also other redundancies in the logic. Use the Carnot map. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. OK, so we've got 6 ones and we've got 4 don't cares. The don't cares are pretty straightforward. It's just pretty much all of the A and B 0. All of the rows where A and B are 0, which is this corresponds to this column, this first column, right? And then 0, 1, 0, 1, 0, 1, 0, 1 is a 1. 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0. Sorry, did I get that? Yeah, I got it right. Yeah, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, and 1, 0, 1, 1. So that's pretty much the whole. That's the whole column, right? Yeah. It's all the rows where A and B are 1 and 0. Right? You see that? 1 and 0, 1 and 0, 1 and 0, 1 and 0. Right? So that actually works out really nice for us because you could create a group of the first and the last column, which reduces all the way down. I mean, it takes C and D completely out because all the C and D values are consumed by that grouping. And A is also covered because you've got A0 and A1. So anything left over there is not B. Right? And then you've got 2 other groupings here, those 2 guys. So this first grouping would be not A, right? Because the not A is consistent there. And not C and D, right? Not C and D, right? And then this one at the bottom would again be not A, right? And C and not D. Okay? Now, the next one asks you to do the minimized sum of a product of sums, which is part D here. Let's scroll down a bit. Find a minimized product of sums. So for that one, remember that you have to cover all your zeros. And the thing that's kind of bad about this one is I've got a nice column of zeros here I can circle. Right? But that's the biggest group I can do for that. So this is A, B, but remember, because we're doing product of sums, we have to negate the individual terms. So this is actually corresponds to not A or not B. So that takes care of all those zeros, and now we just have those 2 guys. And the don't cares don't help us here, right? Because the don't cares are sort of, you don't normally do groupings of 3. At least you can't do a grouping of 3 if you're going for purely product of sums notation. So pretty much we got to have to select these 2 groups. So this would be B is 1, right? So this would be a not B, right? Or C or D, right? Because C and D are both 0 there, right? And so I have to negate them. So they're positive here, C and D. They're not negated. And then this grouping here is, again, is not B or not C or not D. And these are, ANDed together. OK? Any questions? All right. What is the difference between combinational and sequential logic? Uh-oh. Come on back. Anyone know that? Combinational and sequential? Yes?
Combinational will take the inputs that were given to it recently and the past inputs, while sequential or combinational will only take the ones that are current.
Right. Yeah, combinational is a function of the current inputs. Sequential is a function of the inputs in the history of inputs. Now, or you could have said sequential has memory and combinational doesn't. That's an easier way to say it. Sequential.
Still got points taken off.
What's that?
I said the same thing and I still got points.
Okay. Okay. See me after class, then we'll get that fixed. Yeah, that's basically it. It's a little confusing because we also learned that in a combinational logic circuit, there's no memory, but the outputs don't necessarily change as soon as you change the inputs because there's propagation delay. So even though there's no memory in a combinational logic circuit, there's still charge that gets, there's still capacitors that sort of have a, quasi-memory effect. But the real difference is sequential logic has explicit memory put into it in the form of flip-flops or latches, right? Or cross-coupling of gates, like having, I guess if you had any logic circuit where you had cycles in it, right? Like feedback circuit, in which you had a bistable state in there, then that would technically be sequential, even though it wouldn't include any flip-flops. But anyway, that's I'm making it more complicated than it needs to be. OK, consider the circuit below. This one asks for propagation and contamination delay. So this had A, B, then there was a C, and then there was a DE, and then there was this Xor gate, right? The AND gate, the 2-input AND, had 30 and 25. So 30 propagation, 25 contamination. That is an OR gate there, right? Yeah. OK, the OR gate, the 2-input OR, had a 30 and 25. Is that the same? 2-input and 30, 25. 2-input OR, that's 40 and 30. Right? Yep. Then we had a 2-input NAND that was 20 and 15. And then we had the 2-input XOR that was 60 and 40. That one's really slow. Did I do that right? OK, so the propagation delay is the longest path through the circuit. So that would be, if you go along, there's actually 3 paths through here, right? Because you could start with A and B, go through this gate, then through this gate, and then through that gate. So if you start it with A and B, then it's going to be 30 plus 20 is 50 plus 60 is 110, right? If you start with C, you're just going to go through 20 plus, you go through this gate, right? And then this gate. So that's 20 plus 60, that's 80, right? And if you start with D or E, that's going to go 40 plus 60, so that's 100. You guys with me? So you're going to pick the longest one because this is the worst possible case. So this is the critical path. The critical path goes, from A or B all the way through here to Y, right? And so propagation delay of this whole circuit is 110 picoseconds. The contamination delay is the minimum path of the contamination delays. So we're going to basically do the opposite, pick the smallest number. So if we start with A or B, it would be 25 plus 15 is 40, plus 40 is 80. If we start with C, it's going to be 25 plus 40. Sorry, C would be 15 plus 40, right? Is 55, right? And if we start with D or E, it's going to be 30 plus 40, right, which is 70. Guys with me? So if that means that after 55 picoseconds, we're going to get some contamination, right? Potentially. That is the smallest amount of time in which we can change any of these inputs and see some contamination, see some flickering there on some output on some activity on the Y, right? So 55. You guys with me? All right. Yes.
Just you have 70 on the answer key for that problem.
Yeah.
I had 70 on the answer key?
Yeah.
Oh, OK. Well, that needs to be fixed. But if you answered 70 and you got full credit, that's OK. If you got 55 and you didn't get full credit, then come see me. OK. All righty. Any questions about that? So contamination delay, by the way, is it clear what that means? It's the minimal amount of time that you will see activity on the output as a result of changing an input. OK. So this one was just basically just a Kmat problem, which is pretty straightforward. I already selected the groupings for you. So this grouping is, it looks like not A, right? Not A, and not C, right? And this grouping would be A and D, right? If I didn't screw that up, right? OK, so can the circuit glitch when a single input value is changed? According to the book, glitches can happen whenever you change an input that causes the output to leave one grouping and enter another grouping, crossing the boundaries between groupings, right? So yeah, it looks like a glitch could happen because, for instance, if I'm over here and I've got A and B are both 1 and C is a 0 and D is a 1, I could just change A, for instance. So if I flipped A from 1 to 0, that could cause a glitch because I've moved from this grouping to that grouping. I've crossed the boundary between two groupings. The way to fix it is to add a third implicate that overlaps that, prevents that from happening. So if I want to prevent the glitch, I can add this redundant term, which is not C and D, which will cover this whole row and will connect these two groupings together. So it'll be impossible to change just one input. It will be impossible to flip one input and have it cross the boundary between two K-map groupings, right? So adding this term, which is kind of redundant from a Boolean point of view, will prevent the glitch, the little momentary lapse. Yes?
Is there anything functionally different between not C, D, and B, not C, not D? I mean, B, not C, D.
B not C?
B, not C, D.
Oh, B not C, D, this?
Is there anything different than that?
Oh, you mean if you just circled these two instead of the whole row? No. I think that's equally as good.
Okay.
Yeah. Okay, if you had, then that was just an oversight. I was looking for this. If you answered something different, it might have not dawned on me that you were just connecting these two groups through this pair of cells. So that's okay. And that was it. Okay, great. That was it. Any questions? Okay, great. Okay, if you have any questions about the grading, please see me after class. All right, we don't have that much time, but I would like to continue with our lecture. And by the way, there will not be a quiz this week. We'll have another quiz. We'll have our next quiz will be next week. Okay, so this is, last time we were talking about sequential logic. I started out by talking about the components that make up sequential logic, namely latches and flip-flops, right? So we started out with a simple bistable circuit. Bistable means that if somehow you can inject a 1 or a 0 into this Q or Q prime, then this circuit could stabilize in either state, 0 or 1. When I say, and I'm referring to Q, and Q bar would just be the complement of whatever that is, right? This is actually the way that SRAM is built. The only difference is that this circuit has no way to get anything into it. There's no way to set this. You guys with me? There's no way to inject a value into this. If you have this circuit, you have to accept whatever was in there by initially, and then it's stuck in there forever. So in an SRAM circuit, they actually add a transistor here to both of these guys that allow you to connect these to a data line. You guys with me? Now, why don't we look at that? Well, because that's transistor level stuff that we generally stay away from in this class. But basically, each one of these inverters is 2 transistors. You need 2 more transistors to be able to get a value in, and thus an SRAM cell requires 6 transistors per bit, and that defines that's what determines how much level 1, 2, and 3 cache you can have on your CPU. Is the fact that it requires 6 transistors per bit. That's why CPUs have limited amounts of cache. So we talked about the SR latch, which is basically it's kind of another way to build an SRAM style cell, except the inverters are replaced by NAND gates, because a NAND gate is kind of a controllable inverter, sort of, where if you have sorry, those are NOR gates. So if you have a NOR gate and I put a 1 into one of the inputs, that will, sorry, if I put a 0 into one of the inputs, then the other input, in the output basically become an inverter. This allows us to, if R and S, if R is 1 and S is 0, that does a reset where it forces a 0 in here. And if R is a 0 and S is a 1, then it forces a 1 in here. So R stands for reset, S stands for set. putting a 1, 1 is an invalid input, and putting a 0, 0 in there will basically turn it into the inverter thing that I showed you in the previous slide, right? Because if you put a 0 in for R and S, both of these guys essentially turn into inverters. You end up with a cross-coupled inverter. The problem is that it's hard to design with something like that. So generally speaking, well, because you have R and S. So it's a little bit easier if we have a clock and a D, where the clock opens up the latch and allows D to go in. And then if you bring down the clock, it captures whatever the last value, whatever the value of D was when clock went from 1 to 0. You guys with me? So it's like a gate. It's like when clock is high, it's like you raise the gate, you let D go in, and at which point Q is just always D. And then when clock goes down, it traps whatever D was at that time, and so it gets trapped in there. So this is, if clock is 0, it doesn't matter what D is, because Q will be whatever the previous Q was, whatever value got trapped in there, got caught in there. Okay, and then if clock is 1, then whatever D is, it will get transferred directly to Q. Okay. Latches, no one uses latches though. I mean, they're fairly rare. It's more common to use a flip-flop. A flip-flop is yet one more layer of abstraction that we add on top, in which instead of the clock being level sensitive, the clock is edge sensitive, meaning that we're looking not just for clock to be high to capture the input and store it, but we're looking for the rising edge of clock. Right? Now, you guys say, what's the advantage of that? If you capture your D into Q on the rising edge of the clock, the capture time, the time in which you allow your D to come into the circuit, the memory circuit, is the rise time of clock, which is a really tiny amount of time. And you want that time to be tiny because it makes it easier to design stable circuits. Right? You don't want there to be any uncertainty. You want this really short time to take a snapshot of D and capture it inside the flip-flop. You guys with me? So everything else in this whole chapter will assume that we're using flip-flops. So, we cover latches just to say that we covered them, so you understand how you make them and how they behave. But everything from this point on is going to be using flip-flops. Okay, you guys with me? By the way, everything you guys covered in 212, all the registers that showed up in the circuits for 212, the MIPS CPU, those were all the edge trigger kind. Those are all the flip-flop style registers, right? Everything in architecture always assumes that we use edge-sensitive flip-flops and registers. A multi-bit flip-flop is referred to as a register. Everyone with me on that? Okay. So this is a timing diagram that shows the difference in behavior. This is what I just got done saying. A register, if you have multiple flip-flops that are together and they all have the same clock, but each D is a different bit of a multi-bit signal, right? Then it's called a register. This is super confusing, by the way, because a register means multiple things now. A register can mean this, or it could mean a register like you have in machine language, assembly language programming, where when a register is an addressable location in a register file, in a storage unit, a register file. You guys with me? So don't get confused. What's the difference between this register and the registers that you looked at in your 212 class? There's no address for this one. This one, there's no address bits here. This is just input and output and clock. That's it. There's no address. This is just a single value that is there. There's no depth to this. It's not like a table. It's just one value. Does that make sense? I don't know if that's clear. We'll talk more about registers when we get to a little bit later in the semester. Flip-flops, I don't know if I got this far last time. Flip-flops can also have an enable input, which is kind of common. So sometimes you want to So the problem is that the clock is always going. The clock is a this periodic signal, but sometimes you want to be able to capture a value in a register or a flip-flop, but you want to hold on to it across multiple clock cycles, right? You don't want it to absorb a new input on the next clock edge, right? Now, what's an example of that? I'm drawing a blank here. I don't know if you guys, well, you might have not covered this, but in the MIPS processor, there's these high and low registers that get set whenever you do a multiply instruction. And you don't want to set them unless you're doing a multiply or a divide instruction. So that's an example. You have an enable for those, right? What else would be an example of that? I can't think of any off the top of my head. But anytime you want to have a register and you want to hang on to it for a while, you want it to persist across multiple cycles, then you set the enable to low, and then the clock edge gets ignored whenever enable is low. And the way you can implement that is just a very simple approach. You have a mux here that if enable is low, it will just continuously feed in Q every cycle. If enable is high, then it passes D through, right? This, by the way, is similar to what we had on the exam, right? That question with the muxes on the exam where we were using muxes to block or to route data, right? Enable sometimes will just show up in just the regular symbol for flip-flop. So in this case, we have clock, which has this little triangle, enable, which is labeled. D is usually on the left, and Q is on the right. Q, don't know what that stands for. D is data. Q, that's one of those letters in digital logic that's unclear. There's also a JK flip-flop, which we're not going to cover, but JK, I think, is initials of Jack Kirby. I think Q might be Quine. I think this is someone's last name, but it was adopted as a standard letter there. Anyway, I couldn't tell you what it stands for, but it's whatever values in the register. There's also flip-flops that can be reset. Reset is just a way to initialize a register at the beginning. They're usually tied to the global reset. Global resets are usually just connected to a capacitor that's connected to the dang power switch on your computer. So you hit the power or your reset and the button, and that triggers a global reset that just resets all the registers or flip-flops to a known state to 0. So reset resets it to 0. But there's a question about that. When does it happen? If I set reset to 1, when do they get reset? Well, that depends. You can have an asynchronous reset that will immediately set Q to 0, right? And then you can have a synchronous reset that waits until the clock edge, which is normally when Q changes on the clock edge, right? So there are synchronous and asynchronous resets. Does that make sense to everyone? Now, when would you use one or the other? I never quite figured that one out. Asynchronous resets are usually standard. Synchronous resets, I guess the risk there is that you want to reset your computer, but the reset won't take effect until the end of the current clock cycle. So if I have a 1 gigahertz clock, I might have to wait 900 picoseconds for the reset to happen. Well, God, what could happen in 900 picoseconds? Something horrible, right? I don't want to wait that long. I want to reset it right away. So I'll use an asynchronous reset, right? I don't know. I've never seen a case where it mattered, but it's emphasized here. And then there's also a set version where you can, instead of reset, there's a set input where you would it's just like reset, but it sets it to 1 instead of 0. I've never found a case where I needed this in my experience. Okay, so this slide is a little bit out of place. This probably should have been towards the beginning of the lecture before we started getting into the flip-flops, because this is an example of a sequential logic circuit that does not have a flip-flop or a latch. This is called this is an oscillator, a ring oscillator. I left it in here. I thought about taking this out, but I left it in because these are really fun. Back in my previous life when I used to design chips, ASICs, when I designed integrated circuits for fabrication, every time we get a new process, like a new process, like a half micron or 0.18 micron fabrication process, we would build a ring oscillator just to test how fast that technology was. Because the ring oscillator is if you put an odd number of inverters in series, although the rule was always to use a prime number of inverters in series. I never understood why it was necessary to have a prime number. But if you have an odd number, these things will oscillate. Each one of these bits will just continuously oscillate because it's an unstable circuit. So you'll get this thing where x will become, if x was 1, it becomes 0. It'll flip y, which will flip z, which will then flip x, which will flip y, which will flip z, and it'll just keep going. The more of these inverters you have in series, the longer the period of the oscillator will be. But the frequency will depend on how fast the inverters are themselves. So generally speaking, if you shrink your process technology down, if you go from 180 nanometers to 90 nanometer or 45 nanometer or 22 nanometer or 14 nanometer or an 11 nanometer, which Intel is having trouble with, every time you shrink, you're going to get a faster frequency on these ring oscillators. And this is a way that you could, in theory, you could generate a clock signal by doing this. But aside from that, not really practical. OK, so let's see, how much time do I have left here? I'm almost out. OK. All right, so in the next lecture, I will start talking about the really practical application of sequential logic circuits, and that is to build finite state machines, which allow you essentially to create a controller in digital logic, something that keeps track of state and responds to certain things as a function of history. So we'll pick this up on Monday.